Hello and welcome. Today is Tuesday, May 5th. We will go over units 3 and 4 today from the MyAP FRQ series. So let's begin. I believe there's 4 more FRQ questions to do. Starting with this one here. This is Unit 3-1. Alright. So it says the question is a long free response question. Ooh, a long one. Alright. Looks like there's a motor, a string, a block, and it's spinning around. This looks familiar. Do you guys remember what this looks like? In the apparatus shown above, one end of a string of length L is attached to a block of mass M, and the other end is connected to the axle of a motor that rotates, causing the block to move in a circle of radius r. Yeah. Now, it is the flying pigs, but it does have a term. There's a specific term for this type of motion, if you will. I noticed some of the APC students are in here. They're lurking. So if you know, please write it in the chat. What is this called? What is the name of this apparatus? Let's see. Were we causing the block to move in a circle of radius r at a constant speed vt, such that the string makes an angle theta with the vertical. A student wants to use the apparatus to make measurements and create a graph that can be used to estimate the acceleration g due to gravity at the surface of Earth. The student can adjust the motor to achieve different tangential speeds of the block. Ooh, you're close there, Bubble Guy. You're close. Think about the motion. So you're close with the first part. I'm gonna turn it into an adjective. And then the second part, think about the motion. What is the block doing? As a function of time. Anyway. Let's see. Let's start with A. A says the dot below represents the object. Okay, the center of mass. Blah blah blah. Speed at position in the figure. Okay, on the dot, draw and label the forces, not components. So don't draw components. Now sometimes we do those dotted lines to show like mg sine theta, mg cosine theta. If there's a question that is specifically about FBDs, only draw the applied forces on the object, not the net force, but the applied forces on the object, no components. So if there's a section of the FRQ that is directly asking you to do FBDs, only draw the entire whole vector. Now in the process of solving, you might need to break vectors down into components, but that's later. So if there's a section where it's just FBDs, just draw the actual forces. Well, what are the forces? If I freeze time on the side here, this is just flying pigs. So the FBD is tension at the angle or whatever it is, and of course mass mg, mass times gravity downwards, the force of gravity. The centripetal force is not an applied force; it's a net force. Okay, back to the question. Derive an expression for the block's centripetal acceleration AC in terms of m and theta and physical constants as appropriate. Whoa. What do? I need to figure out what AC is in terms of m and theta. Okay, it's going in a circle, blah, blah, blah. So it seems that if I did some sigma equations, it might help. Sigma Fy, we have theta's up here, so tension times cosine of theta, it's cosine because it's adjacent, tension times Wait, did they say T? I started using T. Yikes. Maybe I should use FT. Let's use FT. Yeah, probably. But if you had to describe forces, definitely describe pole forces. So for example, on my APC test, I'm going to have them talk about the FPD instead of drawing one. Ft cosine theta minus mg equals 0, and then in the x-axis we have just one force, tension times sine of theta. I keep using t. Tension times sine of theta is equal to Mach. So we just have to figure out what tension is, plug and chug, and solve for A. Yeah. Tension is mg over cosine theta, and then plug and chug and solve. So we get tension is equal to mg sine theta over cosine theta is tangent, right? Times, or is equal to, oh, I shouldn't do that. Oh, this is messy. Let's try again. Mg over cosine theta times sine of theta, which is tangent theta, is equal to Mach. M goes away. G tan theta, yay. Alright, using the experimental apparatus shown above and the available equipment design, an experimental procedure the student could use to estimate the acceleration g due to gravity at the surface of Earth. Wow, that's a lot. In the table below, list the quantities and associated symbols that would be measured in the experiment and the equipment needed to measure them. Also list the equipment that would be used to measure each quantity. You do not need to fill in every row, blah, 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 blah. Okay. So we're trying to figure out what G is, what gravity is, based on this stuff. So what are the things that we can measure? So when you get this question, you go back to your equations and look at all the variables and see which ones you need to make measurements of, so you can get to G. Of course, you would, based on our formulas here, let's see, things I need. I need definitely M. Now, do I need M? And someone could say, oh, it cancels out. Do I really need it? Well, what I could do it a couple ways. Right. I could figure out what AC is and then figure out what G is, right? If G tan theta is AC, then G is equal to AC over tan theta. And AC is V squared over R, which is also equal to R omega squared over tan theta. So these are the alternatives. You definitely need this. I need this. I would need this, and that should be it. Okay, so R radius. Now, if I know what L is using a meter stick, so I go to my equation, look at my variables, and then think about what I need to make those measurements. I need a meter stick. Omega, my angular velocity. Some sort of stopwatch or a camera. Logger Pro everything. Angle. Well, I could always use trig to find the angle, right? Use trig or protractor. We don't really like protractors. I'm just going to say use trig. So we don't have to worry about theta. Otherwise, I'd have to solve it in pieces, right? The other option would be to figure out what m is. Well, I can't, because now we have a... We're trying to find g, and I don't know what ft is, so therefore I can't do it the other way. I have to do it this way. You can't use g in order to find g. Student wants to analyze... Uh-oh. I don't know if you saw all that. So here it is. G is equal to AC over tan theta. So that's V squared over R, which is R omega squared. For R, get a meter stick. For omega, get a stopwatch. For angle, just use trig. So he wants to analyze data collected from the experiment by creating a linear graph. Uh-oh, graph question. By creating a linear graph that can be used to estimate the acceleration g due to gravity at the surface of Earth. State what quantity should be plotted on the horizontal axis and what quantity should be plotted on the vertical axis to produce the linear graph. So now we need graph where basically anytime you're doing graph, it's either integral or derivative. Well, let's see. Well, let's make g the y value. Or sorry, no, that's not what we want. If I look at this, it says AC is equal to g times. Let me write it this way: tangent theta times. No, that's not right. Yeah. Let's keep it that way. G tan theta, like so. Then this is some sort of independent variable that I can change. Let's go back. So G AC equals G tan theta. Tan theta would be some sort of independent variable. I can get this as a independent. So I'd have to plot every point for different ACs. Actually, you know, typically the AC would be the independent, and tangent would be a result of what AC is. So the faster I go or the slower I go will change the angle. Will change the angle. However, wait, does that really work? What happens when I go slower? What happens when I go slower? Well, when I go slower, there's not as much tension on the string, so this thing droops down, and therefore more of the radius decreases. Yeah. If I go faster and faster, it kind of flattens out and does circles. And not only that, also pay attention to what happens, right? It actually goes upwards a bit. There comes a point where it becomes, when you're going so fast that the circle is all the way up here. So it's also increasing in height. The actual elevation of the horizontal circle is also increasing in height. All right. So get things in. So the goal is to just, if you're doing some sort of, if you're trying to analyze something through a graph, get it to like a slope-intercept form. Get something into slope-intercept form, and then the slope will give you the value you're looking for. So I need a bunch of ACs, I need a bunch of angles, and then eventually this will be the slope. All right. So y equals mx. Now when I'm going 0, when AC is 0, what is my angle? When, well, AC is 0 whenever, well, radius can't be 0, right? AC is 0 whenever omega is 0. So if omega is 0, it means I'm not spinning around, and so I'm just dangling downwards now. And therefore, if AC is 0, then the angle, which is measured from the vertical, is 0 degrees. 0 degrees. Indicate which feature of the graph could be used to determine G, the slope. Alright, we're done with that one. Move it on. Question number 2. The question is a short. Okay, great. System A, B, and C. Let's see what's going on. We have MS, SS, probably a star, and a planet. Alright, UCM stuff. 3 different planet-star systems which are far apart from one another are shown above. So it's important that they're far apart so they don't exert gravitational forces on each other. Otherwise, it would be a very complicated problem. In System A, planet A of mass MP orbits star A of mass MS in a circular orbit of radius r. B has 4 times the mass for the planet, so it's a bigger planet, and C has a bigger star. All right. Question A. The gravitational force exerted on planet A by star A has magnitude of F0. Ooh, F0. Now that is a classic video game. Everyone should experience it. It's one of the best games ever. It was basically Need for Speed before Need for Speed on the Nintendo Entertainment System. Or I could be wrong. I don't know. Was it the shooter game or the racing game? I think F-Zero was the racing game. Chat, go ahead and verify that. The gravitational force exerted on planet A has F0. Determine the magnitude of the gravitational force exerted in System B and System C. It's a racing game. Good, good. All right. Ah, yes, the shooter game that I'm confusing myself with is called R-Type, which is another classic. Okay, so magnitude of the gravitational force exerted on planet B by star B, blah blah blah. Okay, so let's talk about gravity. Yeah, gravity. Recall that. Oh look, it's a sunny side up omelet. Recall that this is the F capital G, which is G m1 m2 over r squared. That's our general equation. The specific equation would be capital G, the universal gravitational constant, times mass of, so let's times mass of the sun. So in System A, the mass of the sun is ms. And times mass of the planet. The mass of the planet in System A is just mp, mass of planet. And the radius for System A is capital R, and it's squared. So F0 is the gravitational force exerted on planet A by star A, determine, which is equal to G ms mp over r squared. Determine the magnitude of the gravitational force exerted in System B and C. Well, let's just plug and chug. So let's see, for B, G, mass of the star is ms still. That's 4 mp, same radius. C, is C the same? C is the same. Okay. What's next? B, how do the tangential speeds of planets B and C compare to that of planet A? In a clear, coherent, paragraph-length response that may also contain equations and/or drawings, provide claims about why the tangential speed of B is either greater than, less than. So not only do you have to describe it, but also compare them. All right. So logically, figure out what it is, and then compare them. So how do we figure out what the tangential speed is? Well, that's Vorb. How do we get to Vorb? Don't just plop the Vorb equation. Well, the Vorb equation is not given in the equation sheet, so don't just whip it out. You can whip it out if there was multiple choice questions, but unfortunately this year there is none. So you have to get to Vorb, derive it. So deriving, you start off with sigma equations. There's only one force, the gravitational force. So let's do it for A at least. Let's do it for A first. G M S M P over R squared is equal to the net well, we're just doing Newton's second law, so mass times acceleration, and the net is mass of the object that is spinning, the object that is rotating, which is the mass of the planet, divided or multiplied by centripetal acceleration, v squared over r. And so this is what allows you to find what v is, and v is independent of the mass of the satellite, or in this case mass of the planet, and it's purely dependent on what the central object is, the star in this case. One of the r's cancels, and so v is equal to square root of gm over r. Okay, what would be different for the other one? Well, the other one would have 4 times the force. For the other one, you'd have this 4 here. Well, with B, the mass of the planet is 4m, so the 4 is on the right side here. And the 4's cancel. And it gives you the same thing. So here's your proof, right? The speed is independent of the mass of the planet. Since A and B have the same mass of the star and it's the same distance, they must have the same Vorb. Let's call it Vorb. Well, this is VT, so even though this is technically Vorb, we're going to call it VT because the question is talking about VT, the tangential velocity. In C, what's different? Well, the force is still 4, except the mass is different. MP v squared over r. So when you square root it, you get the 2. Uh-oh. I feel a sneeze coming along, but it won't actually come out. Whoa! This is the worst timeline. Alright, so equal, and then C is 2 times bigger. The gravitational force exerted on planet A by star A. Okay, we already did that. How do the speeds? Okay. Oh, that was it. Wait, did you guys... Did I not show the derivation? Uh-oh. So if I run through this again, we did sigma equation. The net force is the gravitational force, it was g mm over r squared, and it's equal to mv squared over r Mach. And the right side is the object that is rotating. actually a rotating object. Rotating object. Okay. The mass that you use on the net side or the total side on the right side of the second Newton's second law equation is the object that is actually rotating. And so you get to Vorb in B. Okay, don't forget, this is a classic College Board trick to use the same variable but with a coefficient in front. So the difference is that in B, you have 4 MP instead of just MP. But the forces are the force is also 4 times bigger. The force cancel, giving you the same Vorb. And then in C, of course, you get a 4, and then when you take the square root, you get a 2 out. So it's twice as fast. Okay. All right, let's move on to Unit 4. Unit 4. Rocket equation. Whoa, well, not really. Rocket question. This is a long free response. Students conduct an experiment to study the motion of 2 rockets. In the first experiment, rocket X of mass mr. In the first experiment. Okay, so rocket X. This one here. Rocket X of mass mr is launched vertically upward with an initial speed of v0 at time t0. The rocket continues upwards until it reaches its maximum height at t1. As the rocket travels upward, frictional forces are considered to be negligible. Wow, that's nice. No air resistance. The rocket then descends vertically downward until it reaches the ground at t2. Alright. The figure above shows the toy rocket at different times. Is this the one with the parachute? Don't tell me it's the one with the parachute. Okay, there's no parachute. Because we did one with a parachute, right? I think. The figure above shows the rocket. Okay. In a second experiment, which has not yet been conducted by the student, rocket Y has mass mr. Okay, so same mass. Oh, whoa. No, it's not same mass. Where mr is bigger than little mr, of course. Will be launched vertically upward with an initial speed VO, same speed at t0 until it reaches its maximum height. Rocket Y will then descend vertically downward until it reaches the ground. Okay. So basically we're going to send up 2 rockets, one with a bigger payload, but with the same initial speed. 2 students, if I have that right. Do I have that right? Is V0 the same? The vertical? Yeah, speed V0. 2 students in a group make predictions about the motion of Y compared to X. Their argument is as follows. Oh, look, this is like a tipper's question. Student 1, rocket Y will have a smaller maximum vertical displacement than rocket X, although it's launched upward with the same speed as rocket X and has more kinetic energy than rocket X. Because rocket Y will have a smaller maximum vertical displacement. Wait, what? Because rocket Y will have a smaller vertical displacement than rocket X, I predict that it will take less time for rocket Y to reach the ground compared with rocket X. Oh, okay. So rocket Y will have a smaller maximum vertical displacement. So Y doesn't go as high, so therefore it's going to take less time. Are we losing people? Probably. Student 2, rocket Y will have the same maximum vertical displacement as rocket X because both rockets have the same kinetic energy. Okay. Since both rockets have the same maximum vertical displacement, I predict it will take both rockets the same amount of time. Ignore whether this is important. For A, ignore whether the student's predictions are correct or incorrect. Do not simply repeat the student's argument as your answers. Okay, that's interesting. Which aspects of the student's one reason? Yes, I like these questions. This was actually on last year's AP1 final. These types of questions, where you have people giving their claims and reasoning, but the questions aren't necessarily about who's right and who's wrong. Okay, so they are much more specific. And for example, in this case, it's what about student one's reasoning, not the claim. First, you have to differentiate the claim from the reasoning, and then you dissect the reasoning, and what about the reasoning is actually correct. So now, even though he may be wrong, you have to figure out what part of it could be right. Okay, so why do all this? Well, think of like lawyers. Sometimes you have to dig deep and defend your client, I suppose. All right. So let's dissect student one's reasoning. So let's go back to student one's. So we're not really interested in what he said particularly. Or perhaps we should think about we should think about the problem first before going in. The problem was rocket was launched with some mass, and it goes up and then it goes down. Okay. The rocket was launched at initial speed v0. So we can get to maximum height. What was it called? Maximum height was h. It just says maximum height of t1. So it takes t1 amount of time to reach max height. Alright, so object is thrown upwards. Does the mass matter? Well, I don't know. Let's find out. If I had kinetic energy here, if I talk about energy, kinetic energy here, pegmega there, we get 1/2 mv squared at the start, now is equal to mgh, and since there's no friction or drag, nothing, we're not losing anything. No non-conservative forces are at play. And so the masses cancel. Whoa. Yeah. So clearly the mass didn't matter. Okay. So let's go back to the reasoning and stuff. So let's go to student one. Student one says rocket Y will have a smaller maximum vertical displacement than rocket X, although it is launched upward with the same speed as rocket X and has okay, so the claim part would be this first part, I guess. Rocket Y will have a smaller maximum vertical displacement. That's his claim. What is the reasoning? It's kind of weird how he stated it, but it is what it is. Although it is launched upward with the same speed as rocket X and has more kinetic energy. Okay, so that is still not reasoning, is it? Right? That's kind of like a contradiction almost. No, I shouldn't say contradiction. More like a counter. It's like a very flawed counter argument. Like here is what the opposition's claim could be. So even though this is true, this my claim is true. So we move on to the next sentence. Because rocket Y will have a smaller maximum vertical displacement than rocket X, I predict it will take less time for rocket Y to reach the ground. Okay. So which axiom of student one's reasoning is correct? Chat, is anyone here? Well, some of you are. So why does it take the second rocket longer? Because it says it will have a smaller maximum vertical displacement. I guess that's his reasoning. So reasoning is right here. Now, did he say why it has a smaller? It doesn't say why, so that's that. Nothing. Which aspects of student one's reasoning, if any, are incorrect? Explain your answer. Well, now you get to actually contradict his reasoning. And do you have to explain why? Yeah, you have to explain your answer. So now you can use conservation of energy, show that if it starts with the same velocity, it's going to reach the same height because the masses cancel. Why is that conceptually? Well, it's true that with a bigger mass I would have more kinetic energy, but now there's a force that is pulling me down, right? So the force that is pulling me down, the weight of the object, is also more. So and so similar to how you have like F equals ma, the F divided by m is equal to a. The acceleration for both objects is still g, and so therefore, if you're accelerating downwards at g and you start with the same velocity VO, then it doesn't matter what your mass is. Alright, next up, which aspects of student 2's reasoning, if any, are correct? So what part of student 2's reasoning? Okay, we want to first separate the claim from the reasoning. Student 2 says rocket Y will have the same maximum vertical displacement as X. Okay, so that's the claim. Now let's see if we can find some reasoning. Because both rockets have the same kinetic energy. Okay, so that could be part of the reasoning. Since both rockets have the same maximum displacement, okay, so here's some extra stuff. So they have the same vertical displacement. I predict it will take both rockets the same amount of time. Okay. If you're accelerating at the same rate, of course we know that if you're accelerating at the same rate, starting with the same velocity, it's going to take you the same amount of time, to decelerate to 0, and it's going to take you the same amount of time to accelerate back to the original. This is a nice parabola. All right, so which part could be correct? The part that could be correct is that they have the same maximum vertical displacement. They reach the same height, right? Which aspect of student 2 is incorrect? Which aspect is incorrect? The first part. They have the same kinetic energy. Clearly, they do not have the same kinetic energy. The one with the bigger mass has more kinetic energy. Use quantities reasoning, including as needed, equations as needed to derive expressions for the maximum height. Oh, so now we actually have to do the physics. Let's see, h is equal to VO squared over 2g. Okay. VO squared over 2g. Maximum height achieved by x and y. Express your answer in terms of blah blah blah. Okay, so done. Use quantities reasoning, quantitative reasoning, including equations as needed to derive expressions for the time it takes. All right, now we've got to do time. So now it's a VOVAT stuff. VOVAT. Initial velocity is v. Final velocity is 0. The time it takes for what to reach the maximum height? Oh, reach the ground after reaching the respective maximum height. Oh, reach the ground. I could do it backwards or realize that it's a parabola and it's symmetric. Acceleration is negative gravity, negative g. Displacement is negative h, which is equal to negative VO squared over 2g. And solve for t. So I have d, I have a, I have everything, so I could use any equation. So T1 must be equal to, what should we use? Raphael? Or no, or Mikey? Mikey sounds good. Because I can use VOMMH. Well, let's see, Mikey says V is equal to VO plus AT. Here's our general equation. Time is the change in velocity over change in time. 0 minus VO over negative G. Okay, so it takes that much time to go up. It also takes that much time to go down. Explain how any how any correct aspects of each student's reasoning identified in Part A are expressed by your mathematical relationship in Part B. Ooh. Okay, so wow. So for each student, so I have to go back. For each student, we have to look at what we identified in Part A and then relate it to what we just solved for, or expressed by your mathematical relationships in Part B. So okay, so the equation that we got in Part B was the height equation. The height equation is VO squared over 2G. And then let's take a look at how this could be used. So obviously we go back, then we can actually now state that gravity is the same for both. H is directly related to the square of the initial velocity, and the initial velocity is the same. So therefore, student 1 assume that the rocket Y will have a smaller maximum vertical displacement. Student Y is incorrect because H is directly proportional to VO squared, and VO squared is the same for both. Whereas student 2 got it correct in that they have the same maximum displacement. And then same thing with the time. So now we go back to the time equation. The time equation was VO over G. Again, now T is directly related to, I should say proportional. Let's try again. T is proportional to VO. And since they're both the same, it's going to take the same amount of time. So we go back to what they said. So student 1 was correct in that it will take the same amount of time, and student 2 is incorrect. All right. So the goal of doing this problem again is the part where you have to differentiate the claim from the reasoning, and then careful, don't just rush into the problem and try to just show how much physics knowledge you have. That is not the game. That's not the game you're playing. Okay, it's really about reading the questions correctly and carefully and answering the questions in the short amount of time that you have. Okay? You want to be specific, to the point, concise, but also back it up with actual physical laws and perhaps equations, right? So sometimes people can say wrong things, but the question isn't about what is wrong and what is right. It's more about what evidence did they use that could be right, what evidence did they use that is incorrect, and so on. So the test is a little deeper than just expressing concepts of physics. And because we only have 2 FRQs, I have a very strong feeling that one of them will have something to do with argumentation and where you have to dissect claims and reasoning. All right, is that it? No, there's one more. The question is a short. Okay, that's good. We're going bungee jumping. Whoa, platform, cord, we're falling upside down. Distance is D. and then we stretch it out, and then H. Okay. An amusement park ride is designed such that one end of an elastic cord is fixed to a platform that is a distance d above the ground. The end of the cord is attached to a person of mass m. The cord has an unstretched length of L. We kind of did this bungee cord style problem. Unstretched length L to begin the ride. The person jumps up from the platform with an initial speed VO, as shown in figure 1. What? No, that's not. Okay, whatever. So we go up, and then parabolically we'll go back down. Therefore, when we reach the same height as the platform, our velocity should be negative of what we started with, because it's nice and symmetric. Where were we? As the person falls, the elastic cord stretches and can be modeled much like a spring of negligible mass. Okay. After the cord can no longer be stretched, the person is a distance h above the ground and is no longer in motion, shown in figure 2. The reference position for zero gravitational potential energy of the person, cord, earth system is a distance h above the ground. So they're telling you that the lowest point of this drop is now h0. And the system things is interesting. Person, cord, earth system. I had a question someone asked, like, does heat that you release due to friction and other things stay inside the earth, and so therefore is energy conserved when you have friction? The answer is no. Friction is a non-conservative force. So in order for energy to be conserved, you have to have conservative forces only. And so gravity, or the gravitational field, is able to store the energy itself. Therefore, the gravitational force is a conservative force, and you can save the energy in it. So when it says when Earth is part of your system, just think that Earth is another object with mass, and therefore gravity is at play. The gravitational force is an internal force now, not an external force. All right. So again, at the bottom, h above the ground is h0. The reference position for okay, all frictional forces are considered to be negligible. All right, nice. There's no air resistance and other things. The initial state of the system is shown in figure 1. Find the final state of the system. Oh, and the final state of the system is shown in figure 2. Describe the energy transformations that take place from the initial state to the final state for each form of energy. Identify the object or system that has that form of energy. Wow, okay. So not only do you have to talk about what energy you have, but where is the energy? All right, so we're bungee jumping. Here's our platform. We're going down and we stretch the spring. So here, remember, we jumped upwards. Did we jump upwards? Is that what it says? The person jumps up from the platform with an initial speed VO. So we're going up. So I should draw it like a parabola. We actually go up, and then we go down, and then voila. But our initial point A is here. Final point is B down here. And B is h meters above the ground. So at A, we actually have PEG and KE. Okay. The gravitational potential energy is in the gravitational field. So where do you store where do you store PEG-MAGA? In the gravitational field. Gravitational field. So that's your storage. How should I write this? Stored. So stored in the gravitational field. Where is kinetic energy? Well, kinetic energy is within the object itself, so the person has the kinetic energy. By the time you get to the bottom, remember H0 is actually at B. So you have 0 gravitational potential energy, 0 pegmega at B. So therefore, all of your energy is now PES. And PES is stored within the spring. The spring has the energy. All right. Derive an expression for the spring constant of the cord in terms of D, L, H, V, O, M, and physical constants as appropriate. Now, the distance we traveled is L, the lateral length plus the actual stretched amount. So this is L plus X, where X is the stretch. Natural length, X is the stretch, and therefore the PES energy that I have, 1/2 kx squared, is based on that, X. But I can't use X yet, right? I can't use X yet. Well, I can use little h. What is little h? Oh, what? D, L, H, and V, O, M, and physical constants. Where is little h? Chat, do you see little h anywhere? I don't see little h. There's no mention of little h. You think it means capital H? Well, that is a very big, I mean, the AP test cannot have any flaws like that. That is unfortunate. I hope they don't do this on the AP test. Usually they're much better on the test because you know, they're written by professors and stuff and teachers, and then they get audited. You think it's capital H? There's no capital H as the variables you can see. Yeah, I guess. All right, let's see what we can do. D is the total thing, right? So we said that L plus X is how much you're traveling going down, and D is the total, and D is equal to capital H plus L plus X. L being the natural length, X being the stretched amount, and H being the amount that is above the ground, and D is the total distance from the ground to the top. Okay, so this allows us to find what X is. X is equal to D minus H minus L. Okay, and then just do energy conservation. PES is equal to the original amount, which is equal to 1/2 mVO squared. Remember, we come to a stop, so all of our kinetic energy is gone. mVO squared plus the original gravitational energy. Or how much pegmega did I lose? I lost mg times the amount that I fell, which is L plus X. Okay, so we have X. So we have two terms with X. This is a quadratic, and then, you know, and then solve. Or simplify. Plug and check. I'm not going to do this. You guys can do it. Here you go. Here's X, and then plug and chug. Make sure you distribute. Combine like terms, etc. So you can have a term without x. Make sure you combine it to this. This is a constant. Here, I'll just do one more step, I guess. 1/2 mvs squared plus mgl plus mgx. So there's the term with x. All of this is the constant c term. Now we can, once you plug this in, then you can actually directly solve for k, which is I guess I'll just do it. Too late now. Times 2 divided by x squared is equal to k. So, and then we have to substitute the d minus l, h minus l. Suppose that, okay, let's go back. Suppose that air resistance cannot be ignored. Ooh, now air resistance is not negligible. For the position at which the person has jumped from the platform and the cord reaches its maximum stretch length, how does the stretch length of the cord, when they say stretch length, they mean x, or is it L plus x? Oh. For the position at which the person has jumped from the platform and the cord reaches its maximum stretch length. So stretch length would be L plus x. How does the L plus x, yep. How does the stretch length of the cord in the case with air resistance compare without? Alright, so air resistance is going to slow us down. So we're going to lose more of our kinetic energy. The faster we go, the more air resistance we have. And the force, the drag force itself is dynamic. So the work that the drag force does is also dynamic, meaning it changes as a function of time. As you increase your speed, the amount of work that the drag force is doing increases. But if you integrate every point, if you add up every little tiny point for every time frame and add up all the energy that was lost, that would be the total, of course. Consider taking AP Physics C to do some integrals. Alright, since I'm going to lose a lot of the kinetic energy, I'm not going to go down as much, so it's going to be shorter. Right, you can almost do it conceptually. Think about having like a slinky thing, or not a slinky, like a bungee cord thing, and then you have like a ball, right? If you just drop the ball versus if you throw the ball down with an initial velocity, of course it's going to go further down and it's going to overstretch or stretch the bungee cord, versus when it just falls straight down because of that extra amount of energy, the kinetic energy that is going into the elastic potential energy. Okay, but if you start losing some of your kinetic energy with drag force, then not as much can go into pass, therefore it's not going to stretch as much. Oh, that should be pretty self-explanatory. Alright, thanks for watching. That'll be it. Continue to work on those FRQs. You have about a week left for your AP test. We will see if we can do a walkthrough of the platform. Please watch those videos I talked about earlier. Check your email. The College Board sent you an email. And it has a bunch of YouTube videos. At least watch the first 3. I will also post them on Canvas eventually tomorrow, in case you did not get the email. If you didn't, make sure you log in. Remember, it's the same email that you used for MyAP, so that's the email you want to check constantly. They have demos now, yeah. So we will do a walkthrough of the platform next time, and we'll take a quiz after that. Is there a quiz Thursday? What's my APC doing? APC does have a quiz on Thursday, so actually I'm gonna do regular stuff Thursday for you guys, and then quiz for you guys on Friday. All right, quiz Friday. Okay, thank you for watching. I'll see you next time.